Our second keynote speaker is Dr. Lara Dolecek. When Dr. Lara Dolecek was a young girl in Yugoslavia, she was also a math contest competitor, just like you in the audience. She is now a full professor with the Electrical and Computer Engineering Department and Mathematics Department at the University of California, Los Angeles, UCLA. She holds a BS with honors, MS, and PhDs in the Electrical Engineering Computer Sciences, as well as a master's degree in statistics, all from the University of California, Berkeley. She received the 2007 David J. Sakerson Memorial Prize for the most outstanding doctoral research in the Department of Electrical Engineering and Computer Sciences at UC Berkeley. Prior to joining UCLA, she was a postdoctoral researcher with the Laboratory for Information and Decision Systems at the Massachusetts Institute of Technology. She received IBM Faculty Award in 2014, Northrop Grumman Excellence in Teaching Award 2013, Intel Early Career Faculty Award 2013, University of California Faculty Development Award 2013, and the Okawa Research Grant in 2013, followed by the NSF Career Award in 2012 and the Hellman Fellowship Award in 2011. With her research group and collaborators, she received numerous Best Paper awards. Dr. Dolecek's research interests span coding and information theory, graphical models, statistical methods, and algorithms with applications to emerging systems for data storage and computing. She currently serves as an associate editor for the IEEE Transactions on Information Theory and as the secretary of the IEEE Information Theory Society. Professor Dolecek is 2021-2022 Distinguished Lecturer of the IEEE Information Theory Society. She has served as a consultant for a number of companies specializing in data communications and storage. Please join me in welcoming Dr. Dolecek, who will speak to us about how to correct transmission errors in communication technologies.
Thank you very much, Maria, for this wonderful introduction. It is a great honor to be part of this esteemed program today. Good morning and good afternoon, everyone. Just like many of you, I started as a math enthusiast. As Maria mentioned, I competed in math, and it was already mentioned in our previous presentation. Math is a science, is a queen of all sciences. So as you can see, even a person who started in mathematics, over time I switched to engineering, and now I put various math tools that I have learned over time to good use. So I am a faculty in the engineering department and by courtesy in the math department. I also work with a number of companies and advise them how to build new information systems using precisely mathematical tools that we have been working on. So one subject that is very close to my heart, and I hope you will find it also interesting, is the topic of error control coding. So let's see. So communication systems span a very, very broad range of technologies. Wireless communications, something of course all of you are familiar with. This refers to, for example, your cell phone communications. Internet, of course, yet another technology that we all use every day. Computer chips, perhaps something that you don't actively think about, but still use every day. It's part of your laptop, for example. Data center is something that is out of sight, but it's a place that stores all your Instagram and Facebook photos and so forth, so you can access them quickly, even though you have made them 10 years ago. Blockchains is something that's been in the news lately on the account of new ways of storing cryptocurrencies in particular. And satellite communications is one technology that enables long-range deep space communication. So what do all these systems have in common? Of course, they are all very advanced, very sophisticated technologies, and they have to deal with all kinds of issues that describe them. What is actually common to all these technologies is they all transmit digital information over imperfect mediums. And what that means is that we can actually create a really nice and simple and abstract mathematical model that describes all these systems. So that's what we're going to do today. So suppose you want to transmit raw data. So let's represent this raw data as a sequence of zeros and ones. It's a binary sequence. This is how all these aforementioned systems work. You need to transmit this sequence over a noisy channel. So what you see on the receiver side is some version of this. So some bits got flipped in this example, and I'm marking them in red. But of course, in practice, we don't know which bits got flipped. And in the absence of any other changes to your sequence, we would not be able to figure out what was the intended message. What we do instead in practice, we transmit what we refer to as coded data. So now we have enlarged block diagram. So at the beginning, on the transmitter side, this data source is enriched by an added redundancy. And then this data source plus its redundancy is sent over the same noisy channel. And then on the receiver side, we decode it using this redundancy that we had carefully placed in to infer the message. So today, I will take you on a journey through coding theory, and we'll see various examples of how this is done in practice and perhaps what the future may hold. So I'm going to start with repetition coding. So this is an example of simplest form of coding where we repeat each message bit 3 times. So let's see. So I start with the message bit. I'm going to simply refer to it as M0. And then I repeat it 3 times. So I have 3 M0s. If the initial bit was a 0, that would translate into a triplet of zeros. If the initial message was 1, it would translate into a triplet of 1s. And then we sent this triplet, instead of the original bit, we sent a triplet over the channel. So our valid messages are 3 zeros and 3 1s. This scheme is actually pretty good already. It can detect up to 2 errors in transmission. And what do we mean by that is the following. Suppose your coded message is 3 zeros. You send it over a channel, which we said already is noisy, so it can flip some bits unpredictably. And now instead of seeing 3 zeros, we see a sequence 0, 1, 1. We don't know which bit got flipped, but we know that 0, 1, 1 is not a valid message, so we can immediately say, hey, wait, this is not what was the original message, so we can detect the presence of these errors. We cannot detect all errors. In fact, we cannot detect 3 errors. If, say, 3 zeros were transmitted and we sent it over a noisy channel, but it was a bit unfortunate and all 3 zeros got flipped to 3 1s, this would now look like one of the valid code words, valid output messages, 111, then it would be an undetected error. So repetition code, therefore, can detect up to 2 errors, so 1 or 2, and no more than that. In terms of how many errors can they can correct 1 error. So let's see how that works. So again, let's start with a sequence of 3 zeros. We send it over a noisy channel. So 0, we now receive 0, 1, 0, say. Here that 1 is marked in red, but again, we don't know which bit was flipped. But we can act on majority rule. So majority rule will tell us that whatever the bit that occurs most frequently in this sequence of 3 bits, that's the one that's going to win. So that's what we refer simply by majority rule. So then we will say that this parity P1, the first parity here is in error, and then we just flip it to 0 to 1, and we therefore can declare that indeed the intended message, coded message was 0, 0, 0. So this repetition code can correct up to 1 error, and it has what we refer to as code rate 1/3, and the notation is 1-3 repetition code here, because we take 1 bit of information and we encode it into 3 bits of coded message, and the ratio of these 2 numbers is 1/3. But then that also means that redundant information is transmitted 2/3 of the time. What are some other options? Even though repetition codes are very simple, and you can say perhaps even limited, they are actually quite broadly used. In fact, computer chips, even to this day, use some form of repetition codes. So let's take this one step further. I'm going to next describe what is referred to as a Hamming code. So now we're going to take 4 message bits, and we are going to label them M0, M1, M2, and M3 for these bits. Then we are going to append 3 parity bits for a total sequence of length 7 bits. So our message is of length 4, our code word or coded message is of length 7. And the way this works can be nicely represented using a Venn diagram, which I'm sure all of you are very familiar with. So we're going to put M0 in the middle here in the three-way intersection. We are going to put M1, M2, and M3 in the pairwise intersections, and then parities P1, which tells us that a parity P1 involves bits M0, M1, and M2, P2, which involves bits M0, M2, and M3, and P3, which involves bits M0, M1, and M3. So what in fact this means is that this first parity P1 is going to also be a bit, and it's going to be described as M0 plus M1 plus M2. So this is going to be a summation of zeros and ones, modulo 2. So therefore P1 itself is 0 or 1, and the value depends on the values of M's. And same is true for P2, just this different combination of M's, and P3, which is also yet another combination of these M's. So suppose we have the sequence that is the input message 1, 0, 0, 1. And then we can see that since M0 is 1, M1 is 0, M2 is 0, we sum them up, modulo 2, we get that P1 is 1. And then we can do the rest for the this choice and get that P2 is 0, P3 is 0. And that is indeed what we append to create this message of length 7 bits. So let's see how well this Hamming code does in terms of detection and correction, just like we did for repetition codes. So first, it can detect up to 2 errors in transmission. And let's see that. So here's that Venn diagram one more time. And let's go back to the example that we just described. So we have a code word that is 1001, 100. We send that channel, we'll use this as an example. We send that through our noisy channel, which may flip bits. So the bits that got flipped in this example are those that are marked in red. And again, we don't know which bits got flipped. That is what we are trying to figure out. What we do in this case, we are going to compute syndromes. And syndrome is going to be a certain calculation on these received bits, which are the potentially altered versions of the original bits. So our first syndrome is going to be M0 hat, which means what the received version of M0, M1 hat, the received version of M1, M2 hat, received version of M2, and then P1 hat, a received version of P1, and that is taken modulo 2. We do the same thing for the second syndrome, and then we do the same thing for the third syndrome. Let's see what we have. So since this one is 1, M1 is 0, M2 is 1, and then P1 here, what is received is 1010. We sum them up, take the modulo 2, we get E0 for the syndrome S1. For the syndrome S2, based on this formula here, we get value 1. And for S3, again, based on this formula, we get value 0. So we have now a syndrome that is 0, 1, 0. And as you can see, there is one of them that has value 1, and that gives us a clue that something went wrong. And this is how we, in fact, detect errors in transmission. In fact, what happens is that if S1, S2, and S3 were all 3 zeros, that means P1 was in agreement, or rather the received version of P1 was in agreement with what the actual function it describes in terms of S, that P2, received version of P2 was in agreement, and the received version of P3 was in agreement. That means S1 and S2 and S3 would have to be zeros, had there been no mistakes during the transmission. But if anything else we receive for this sequence of S's, we would conclude that the error in transmission had occurred. And this is one example, 0, 1, 0. That's what we say here. But there is a limit. And in fact, what happens is that 3 errors could go undetected. In this case, just by an unfortunate choice of which 3 bits got flipped, the ones that are marked in red here. As it turns out now, S1 is 0, S2 is 0, and S3 is 0. And the reason is that this ended up being in another code. So this would be an example of undetected error. Let's now see how well our code can do in terms of error correction. This code can correct one error during the transmission, and let's see how. So again, going back to our Venn diagram, and again, our running example, 1001, 100. We send it through the channel. Let's say one bit got flipped. We computed those three syndromes as before. And as it turns out, so 1, 0, and 1 here for this particular example, as it turns out, we can actually figure out which of these bits was wrong based on these syndromes. The way to do that is, so we can figure out that the only way this could have happened is if you assume that there is only one bit that was wrong, the only way this could have happened if it had been M1. There is no other way to get this result. And in fact, what we do in practice in some perhaps a little bit more efficient way, but conceptually similar to this, we do something that is known as syndrome decoding. So in repetition coding, we did majority rule. Now we are going to do syndrome decoding because we have these three equations. So if syndrome is 3 zeros, we'll conclude that there is no error. If a syndrome is 111, we will say that M0 is an error because that is the only way that we could have received that particular syndrome is if indeed M0 was the one that got flipped. And then you have choices for all the other a total of 7 positions. And in fact, we can populate this table. So for the total of 8 for 8 choices of the syndrome, there is 8 values we can have for this triplet. And since, for example, when we say here that if the syndrome is 101, we say here in the table, M1 is an error, which is consistent with what we described earlier. So this was an example of a Hamming code with parameters 4 and 7. As it turns out, Hamming codes can be built for other lengths as well. And with that, we're going to introduce another way of looking at the code. So we said already that P1 and P2 and P3 are described using these 3 congruential equations that are functions of M's. But we can also write this in terms of a parity check matrix. So this P1 being M0 plus M1 plus M2 mod 2 would also say is equivalently represented in this matrix stage, which we refer to as the parity check matrix. So 1 times M1 plus 1 times 1 plus M0 plus 1 times M1 plus 1 times M2 plus 1 times P1 has to be 0, because whatever value modulo 2 this is would have to agree with the value on the left. And then we can populate the rest of this matrix. So because we have 3 parities, we have exactly 3 parity check equations for H. So this is a matrix stage, which represents the parity check equation, the parity check matrix associated with this Hamming code. And in fact, you can observe that this parity check matrix H has 3 rows because we have 3 P's, and it has 7 columns. There is 8 possible columns that have of length 3 that have zeros and ones in them. We excluded the old ones because that would make a bad code. And so there is 2 to the 3 minus 1 of them here. So there's 7 of them. So we say here that H contains all non-zero binary vectors of length 3 as its columns. And that's where these parameters, in fact, came from. 7 is 2 to the 3 minus 1. That's your code word length. And 4 is the length of the message, which is 2 to the 3 minus 1, and then minus this 3. 3 is the number of parities that we can have. And in general, we can actually have a code whose length is, for some choice of a parameter S, 2 to the S minus 1, and K is the length of the input message, which is then 2 to the S minus 1 minus S. And in that case, H is going to be a matrix whose columns are all non-zero vectors of length S. For example, you could build an 1115 Hamming code, which is also used in practice, So you would have 15 columns in this H. There will be 4 rows. In each of these columns of a length 4, we are cycling through all possible choices except for the all zeros column, which I said before, we always exclude because it would make for a bad code. All right. So this code, in general, we can express its code rate in terms of the parameters k and n, and Hamming code, which has parameters 4 and 7, would have a Hamming rate. Hamming code would have a rate of 4/7, and code with parameters 11 and 5 would of course have rate 11/5. Can we do more than one error? So let's consider the case of 7 zeros. We send this over a channel. What we receive is the sequence Y. We have these 3 parities. We're going to go back to the example of 4/7 Hamming code here. We compute this syndrome, which also can be viewed as a linear equation in terms of product of the matrix H with the vector Y transpose, where Y is your received sequence, taken modulo 2. So we use a lot of linear algebra in these kinds of things. So suppose one bit got flipped, the one that is marked in red here. So what we do, we compute this syndrome. So you have your parity check matrix H, you multiply it by what you receive. And this one here, actually what it does, it isolates that column. So it does indeed correspond to the 4th column in H, which is a 0, 1, 1, and that is what you get here. So here, M3, we can conclude as a result, based on the table for syndrome decoding that we already had, is that M3 is an error. But as it turns out, by virtue of us allowing for every possible column except for the all zeros, we would always have a situation like this, where we have 3 columns whose sum is a 0 modulo 2. So here in this case, when we had 1 bit flip and our syndrome was a 0, 1, 1, as it turns out, this sequence, which had undergone 2 bit flips, would also result in a syndrome of the same value, 0, 1, 1. And that is precisely because of how we had constructed this H here to allow for this summation of these specific 3 columns to be 0. And so therefore, we can conclude that the Hamming codes cannot correct 2 errors. They can correct 1 error, but they cannot correct 2 errors. They're more flexible in terms of rate compared to the repetition codes. They're more efficient that way, but this is basically the best they can do. And in fact, this is not just true for the 4/7 code, it is true in general, again, by virtue of having those related vectors in column vectors in H. Again, we can isolate these 3 columns. And if we assume that the all 0 sequence is transmitted, depending on what a received message was, we would always have the same syndrome in the case of this particular case of 1 bit flip here in this row or 2 bit flips in this row. Again, it would be an example of a same syndrome. And that is something that is going to be true for all Hamming codes. Again, 2 errors cannot be corrected. And because H has all non-zero vectors of length S, we would always, no matter what the choice of the parameters of the Hamming code is, we would always have this triplet. So it seems like there's not much that can be done, but not to despair. There's a lot of work that has been done since the early days of coding theory. Even though Hamming codes cannot correct more than 1 error, they served as a stepping stone for much more sophisticated solutions, and I will describe one of them next. So we've seen an example of a parity check matrix. Now I'm going to take this one step further. So now this parity check matrix is going to be of size 20 by 25. So we have 25 coded bits and 20 parity check equations that are organized as rows in this matrix. We call such codes where they have very few ones in matrix. We call them low density parity check codes, or LDPC for short. As you can see in this matrix, there is only every fifth really is a 1, but they're organized in a special way. So what the top row, for example, tells us, because of the where the 1 is, it means 1 times C1 plus 0 times everything else, plus 1 times C6 and so forth, plus 1 times C11 plus C16 plus C21 has to be, when we take mod 2, it has to be 0 if code word is for any valid code. What it actually turns out for LDPC codes is there is an alternative representation. So in addition to this parity check matrix, which we have already seen in the context of Hamming code, we can also represent this using what is known as a tenor graph. So in this tenor graph, there are 2 sets of nodes. There is variable nodes that are marked as circles, and then there is check nodes that are marked as squares. And in particular, columns of H are squares in the graph, and rows of H are circles in the graph. So here, the top row in H is the leftmost check, which we just described. But this also tells us that there is an edge between connecting C1 to this first check, and an edge connecting C6 to that check, and C11 and C16, C21, and so forth. And now, once you have H, you can build a tenor graph and vice versa, they're equivalent. We will say that the checksum, if it's 0, this check is satisfied. And if the checksum is 1, the check is not satisfied. So all code words will have the property that all of their checksums will equal 0, i.e. that all of their checks are satisfied. And that is a very nice property that we can exploit during the decoding. So now I'm going to describe yet another type of decoding that is quite well suited for codes of this type. So now let's talk about message passing decoding of LDPC codes. Again, we will assume that the all zeros code word was transmitted, and that received sequence assume it has some zeros that got flipped to ones. So I'm not marking all the zeros just to not overly clutter the image. Just assume that the ones that are marked in red are the ones that got flipped and everything else stayed as is. So let's see how this message passing works. So first, in the first iteration, variable to check messages are the values of that variable node. So if a node has value 0, it simply transmits a 0 to its neighboring check nodes. If a node has value 1, that bit has value 1 out of the channel, it sends that value 1 to its neighboring check. And that all the nodes do that. So those are variable to check messages. Then checks process the information that they have received from the neighboring variable nodes. So in particular, this first square, its own checksum will be 0 plus 0 plus 0 plus 0 plus 0, 5 zeros. So I'm only highlighting the very first one, but all of them, in fact, are also zeros. And this first checksum is satisfied, so I'm going to mark it in gray. The second checksum, on the other hand, is not satisfied because its value is 1. By the presence of a neighboring variable node whose value is 1. But checks that are not satisfied, they would like to be satisfied. So what they're going to say is they're going to tell their neighbors, you need to flip your value. I'm not satisfied with it. Check doesn't know which of its neighboring variable nodes is wrong. So it's going to send the flip sign to all of its neighbors as follows. So, for example, this check node not being satisfied is going to send a flip signal to all of its neighboring variable nodes. And then all the checks do the same. So now variable nodes receive signals from all of their neighboring check nodes, and then they act on the majority vote. We've seen a simple example of majority in the context of repetition code. Now we are doing this on a by-bit basis. So based on this majority vote, certain variable nodes are going to update their values. So you can see immediately that there is precisely these two variable nodes have more flips than stays. So those are the ones that are going to update their values, since all of the majority of their neighboring check nodes told them to flip. So these two are going to flip. And that's the end of the first iteration. Now in the second iteration, what we have is a sequence of all zeros. And this is the values that indeed our variable nodes are going to send to their neighboring check nodes. And of course, it is easy to see since all the messages are all zeros. Checksums at every check node is going to be sum of zeros modulo 2, which is a 0. So all the checks are satisfied. And what it means is we have arrived at a code word and we have successfully decoded in 2 iterations. So this was an example of 25 coded bits, and we were able to resolve these 2 errors. In practice, LDPC codes are thousands of bits long. They can correct hundreds of errors. And just to give you an order of magnitude reference relative to the Hamming code, which we described earlier, so the LDPC codes can improve by several orders of magnitude in terms of their performance. LDPC codes are nowadays used in many, many different applications. They are the state-of-the-art solutions for hard disk drives. Currently, hard disk drives store reliably over 12 terabytes of data on a 3.5 square inch drive. And this is over 10 to the 13 bits. And none of that would have been possible had it not been for the implementation of LDPC codes. They are also state-of-the-art solutions for wireless communications, and 5G is most recent technology that enables transfer of data at over 20 gigabits per second. And this is just enormous amount of bits per second that is just very hard to even imagine. And again, this is something that is in part enabled by these implementations of LDPC codes. But this story, again, doesn't end here. And in today's journey, we learned about repetition codes, a very simple type of coding that uses majority decoding. We also saw Hamming code with syndrome decoding, and we also saw LDPC codes with message passing decoding. But many other types of codes are currently being actively investigated, and you may hear terminology like polar codes, spatially coupled codes, quantum codes, and even some new ones. And these solutions are actively being developed to meet the increased needs of the digital revolution. Just going back to the pictures we had on the first slide, and all of them desperately need mathematical minds like you. And I do hope that some of you will go on and pursue your research in this domain or related fields. And some parting words. Since we talked about Hamming codes, I just want to mention Richard Hamming, who is a mathematician like you. He was also a father of coding theory. He was also very prolific. So Hamming codes are named after him. You may have also heard of Hamming filter, Hamming distance, all this named after him. What was Hamming also known for was a man of very wise words. So I'm just going to share some quotes from him that I personally found very inspirational. Here's one: luck favors the prepared mind. And the second one: if you do not work on important problems, it is not likely that you will do important work. So you guys have enormous talent. Obviously, you're here, the best of the best, and choose your problems wisely, and sky's the limit. And I would like to refer you to his book, which has been published a long time ago, in fact, which is The Art of Doing Science and Engineering, Learning to Learn. And you will find gems like this in his book there as well. And thank you very much for your time.
Okay, great. Thank you, Dr. Dolecek. That was an awesome talk. I personally love coding theory and information theory more broadly, so thank you. And in fact, we just got a message from one of the students saying something like incredible presentation. Yes. Well, let's see. Students, by the way, feel free to ask a question in the Q&A box. Right now, the Q&A box is empty, so you can fill it. But in the meantime, let me start with my question. You know, at your last slide, you talked about future directions. I wonder if you could say a word about a topic in coding theory that you're pursuing right now.
Yes, and thank you. I was hoping you would ask that. So I'm very excited. This is certainly very close to my heart. I am a mathematician in disguise, I guess would be the word. So my home is an engineering department. But what I really do is math. So as you can see, there's many, many different ways in which you can do math, be successful at it, and have a lot of impact. So some of the things I'm particularly excited about now is developing coding theory for future quantum communications and networks. And that is going to quantum systems. This was in the news, quantum computers that were pioneered by Google a couple of years ago. This is something that's happening very much so. And quantum communication is something that will enable very secure and very fast data transfer. And however, like every other technology, it needs to operate under noisy mediums. But it has its own unique challenges, and we hope to contribute to resolution to some of these challenges. Another thing I'm also working on is coded for distributed computing. So this goes back a little bit to data science, which was one of the subjects that was already mentioned today. When large-scale data processing needs to happen, it typically needs to involve many different computers distributed all over. And in order to do that efficiently, and you may expect that some of these computers may fail, unsurprisingly, coding theory also plays a role. And for that, we use something called erasure coding. And to protect computations, we use coded computations. So those are some examples of some of my recent research endeavors that that me and my research group are currently working on.
Okay, wonderful. In the background, I see a photo of UCLA. If you'd like, you can say a little word about UCLA, and is it a good place for our students to consider attending?
Yes, thank you for that too. So I know you guys are all brilliant and really accomplished, and you have many choices of the universities that you can go to, but I do encourage you to come check out UCLA. It has an excellent math department. It also has a great School of Engineering, new data science program. We have a variety of topics to choose from. Student life is great. And if you do end up coming here, please stop by my office and say hello.
Okay, wonderful. By the way, have you worked with undergraduates before, perhaps in a research project?
Yes, I always have undergraduates, even now. I mean, every year I take on several undergraduates who do research with me. Many of them have published, and most of them end up going to graduate school, pursue PhDs at top institutions. So I always look forward to having talented undergraduates in my office. So maybe one of you will end up working with.
That would be very cool. So let me back up. Our students are in high school. I wonder if you could think back to your high school years and share, a little bit about your journey. How did you go from a student in the former Yugoslavia to where you are now, a distinguished professor?
Thank you for that question. So like our previous speaker, so I was also from a third world country, and I was also in a minority ethnic group. So I actually fled because of the persecution. And this was, if you're too young to remember, but there were Balkan wars in the late 90s. And that was the period when I left myself. And what really got me into a good school in America was the fact that I had previously competed in math competitions in my home country. And I was on the national team ready to go to the math Olympiad. But then the borders closed and that never happened. So I was on the team that never competed. But nonetheless, that really helped my resume and helped me, even as a girl, stand out from the rest. And I was accepted to Berkeley as an undergrad, and that was a wonderful experience. And I just continued pursuing things that I enjoy and trying to do my best in making this world a better place.
Okay, wonderful. And I see a couple questions. Actually, they're in the chat box. You can also ask in the Q&A box too, but since it's here, this is a question from Ramya Iyer, and I'll just read it. How do you see the future of quantum computing error correction evolving in the next few years, especially since error correction is a large section in quantum computing?
So there's a lot of ways in which error correction enters communication networks. It is not just communication systems, I should say. It's not just for quantum computing. The problem with quantum error correction has been around for a while, and one may argue that it's, if you ask Google, they will tell you that they already solved that problem. But there is other places in which error correction plays a very important role when it comes to quantum information systems. And nowadays we are building quantum communication systems and quantum networks. Other countries other than ours have already taken a leap and implemented this. USA is still working on it. And the role in generating, for example, quantum key distribution, which is QKD for short, which is that key that different users, you may refer to them as Alice and Bob, for example, need to agree on. That's something that needs to be protected as well over these quantum style channels. And this is the domain that desperately needs some type of error correction coding that is tailored to this domain.
Okay, and continuing on with quantum computing, we've got another question. If quantum computing can break crypto algorithms in milliseconds, what do we do about security?
Again, so error correction is not something that is unique to computing. It is going to come in other types of quantum information systems. So this is something that is very much in terms of breakage. It's something that is very much in mind of many scientists, and everybody's actively working on it.
Okay, awesome. And maybe a final question then. If you could, again, think back to your high school days. Would you have any advice for your younger self, and would you do anything different?
I think I'm just going to echo what was said before, and go at it. Don't be afraid. Life will work out. Wonderful things will happen, and do your best.
Okay, good advice, Dr. Dolecek. Thank you for your presentation and for
the invitation.
Answering these questions. Okay, I think we'll turn it back to Maria, who will introduce our next speaker.
So as it turns out, my background is also computer and systems engineering. So this presentation area was near and dear to my heart too, Professor Dolecek. Thank you for sharing your life story, and good luck with your intriguing future quantum work.